So hello students, finally we have come to the final lecture of the chapter Work per Energy. The final topic is our energy. In this video, we will discuss about the types of energy, the units of energy, the conservation of energy, and about the work energy theorem. So let's start with the energy part. Energy. What is energy? What is energy? The simplest definition is it is the capacity to do work. The capacity to do work. The more energy you have, the more work you can do. So energy and work are equivalent to each other. So since they're equivalent to each other, there are a lot of characters that are same. Number one, energy is scalar quantity, just like work done. Energy is a scalar quantity, just like work done. Number two, unit of energy is again same as work done, that is joule. The SI unit of energy is joule. Now, there are a few commercial units or bigger units of energy too. Bigger units of energy are watt hour and kilowatt hour. Clear? Watt hour and kilowatt hour. Now, for the conversation, let's move to the next page. Watt hour to joule. Let's start. One watt into 1 hour is equals to 1 joule per second into, convert the hour into second, that is 3600 seconds. So ultimately 1 watt hour is equals to 3600 joule. That is the first conversion. Number 2, kilowatt hour to joule. One kilowatt into 1 hour is 1000 watt into 1 hour, which is equals to 1000 joule per second into 3600 second. So second and second cancel, that is 361234 joule, or we can say 3.6 into 10 to the power 6 joule. That's 1 kilowatt hour. The two conversions that are very much required. Please go through them once. Next, Another unit is thermal unit of energy. Thermal unit of energy is calorie. You all have heard about this. Calorie, short form cal. Conversation: 1 calorie is equals to 4.186 joule, or we write approx to 4.2 joule. 1 calorie is 4.186 joule, or approximately 4.2 joule. Another unit is the electronic unit, means where electrons are involved. It is EV, sorry, that's the full form, electron volt, short form EV. Electron volt. The conversation is 1 electron volt is 1.6 into 10 to the power minus 19 joule. Clear? What is the definition of 1 electron volt? It is the energy gained by an electron when it is accelerated through a potential difference of 1 volt. So if you send an electron into a chamber where the potential difference in one is 1 volt, the acceleration that the electron will take place is known as 1 electron volt. Please go through this. Okay, now let's come to the third part, that is mechanical energy. Now, in your syllabus, the mechanical energy is divided into two broad parts. The two parts are potential energy, short form PE, and kinetic energy, short form KE. You all know these things already. Potential energy PE, kinetic energy, and KE. The potential energy is again subdivided into two more parts. This is gravitational potential energy. Short form GPE. Formula GPE or U, both. U equals to mgh. Next is elastic potential energy. This happens in a stretched spring. Due to change in length. The kinetic energy, the kinetic energy. Now, how to approach the kinetic energy? We know that work done and energy is equivalent to each other. We know that the basic formula of kinetic energy is half mv square. But how to achieve the formula? Why is it half mv square? Let's start with the derivation first. We know that work done is equals to, energy is equals to work. And we know that work is equals to force into displacement. We know this. Now, let's start. Therefore, energy equals to force is mass into acceleration and displacement is s. Next, let's keep this over here. Let's move to Newton's formula. That was v square equals to u square plus 2as. Let's assume that initial velocity is 0. Let's assume that initial velocity was 0, u was 0. So therefore, s comes as 1 by 2 a into v square. That is your s. Putting this value in this s, E becomes equivalent to m into a into 1 by 2a into v square. So a cancels. So energy is half mv square. That is how the kinetic energy formula is derived. Okay. Now, if you are asked to write the types of kinetic energy, there are broadly 3 types of kinetic energy that needs to be studied, or is generally asked, I would rather say. Number 1, translational kinetic energy. When a body is moving in a straight line, body moves in straight line. Rotational kinetic energy, body moves in rotational motion. And the last is vibrational kinetic energy. It is present inside the molecules or the electrons when they are vibrating. Present in a vibrating body, or particle, can also say particles. So the broadly 3 types of kinetic energy. Please go through this chart once. Now, let's move to the next topic, that is relation between kinetic energy and momentum. Momentum is denoted by P. Relation between kinetic energy and momentum. Now, momentum is mass into velocity. We all know this. And kinetic energy is equals to half mv square. The two main parts of the derivation, momentum and kinetic energy. Now, we have two relations for this. The first one is mass-based relation. And the second is velocity-based relation. We have two relations for the between kinetic energy and momentum, mass-based and velocity-based. So let's start with the first one. See. So how it is done? Momentum is mass into velocity and kinetic energy is half mv square. Now all I will do is like this. I will do it. Kinetic energy is I will multiply both sides with mass. That is, let me write kinetic energy only for K. Kinetic energy into mass, that is half into m square v square. Multiplying both sides with m. Let me write it down. Multiplying both sides with m. Clear? Now, therefore, Km is equals to half, we can write this mv whole square, where mv is equals to your momentum square. So therefore, P is equals to root over of 2 km, the first relation, the mass-based relation. Momentum equals to root over of 2 km. Now let's come to the velocity-based relation. In this one, again, momentum is mass into velocity and kinetic energy is equals to half mv square. All I will do is, I will write kinetic energy as K and I will write half mv into v. I will break the v square into v into v. V into v. Now, kinetic energy is half, mv is momentum into velocity. So momentum will is equals to 2k by v. The velocity-based relations. So between momentum and kinetic energy, you have two type of relations, mass-based relations and velocity-based relations. Everyone, do go through it once. Okay, now let's move to the next topic, that is the work energy theorem. It's a very important topic. Work energy theorem. What is work energy theorem? When work is converted to an energy, or the interdependence between work and energy. What kind of energy? Kinetic energy. Because make sure whenever the body is in motion, only then the body is doing work, and motion means kinetic energy, whereas potential energy means body is at rest. So, okay, let me write it down for you. Kinetic energy for motion and potential energy for rest, so that you don't forget it. So work energy theorem. What is the thing? Now, let's assume that you have a body at point A of mass m. You are moving this body to point B, mass remains constant with a distance s. Now obviously, to move a body from point A to point B, you need to apply some kind of force. Therefore, the work done will be what? Force into displacement. The simple, no, basic thing. Now, if the body was moving, then the body must have had some amount of initial velocity u, and when the body reached at B, there must have been some kind of final velocity v, right? In motion, we consider kinetic energy. So what was your initial kinetic energy? Ki is half m u square, because initial velocity was u. Similarly, what was your final kinetic energy? Kf, half m v square. So what is the change in kinetic energy? That is delta K. Delta K is Kf minus Ki, final minus initial. So that comes out to be as half mv square minus half mu square. If we take common half m, that's v square minus u square. That's delta K, or change in kinetic energy. Now let's take the help of Newton. So what Newton said is v square equals to u square plus 2as. Therefore, v square minus u square equals to 2as, right? Also, v square minus u square by 2a equals to s. That is what you were getting, right? So, but in this place, we need v square minus u square. What is v square minus u square? 2as. So if we put delta K is equals to half m into v square minus u square is 2as. These two cancels. What is coming as m into a into s? Now what is m into a? It's force, and s was displacement, which is equals to work done. So therefore you can say that work done is equals to change in kinetic energy. That is the work energy theorem. Work done is equals to change in kinetic energy. So the general format is W equals to half m v square minus u square. You will get this type of sums that will require this formula. Those sums are very important. So just go through this once. Okay, now let's move to the next topic, that is conservation of mechanical energy. Conservation of mechanical energy. How to do this? It's a very simple derivation. Let's move with the derivation. Let's assume that you have an object at this height, on the top of a building. The height of the building is I am taking it as h, the total height. Point A, this is point A. Somewhere middle, not exactly middle, this is point B. And on the ground, this is point C. This is ground. So you were dropping an object from a certain height. Okay, you are dropping an object from certain height. Let me now divide the point. Let's say from A to B, this is x distance. Let's take this to be as x. So the other half is h minus x. Okay. Now, when the body was at point A, the body was still at rest. And we know that when a body is at rest, it has only potential energy and no kinetic energy. So at the topmost point, you have potential energy that is maximum, that is mgh. And you have kinetic energy which is equals to 0. Because the body has still not started to move. So according to this concept, potential energy at point A will be maximum, that is mgh, and kinetic energy at point A will be 0. So therefore, total energy is always potential plus kinetic. So therefore, total energy comes to be as mgh because Ke is 0. At point A, total energy is mgh. Now let's take at point B. When the body has traveled to point B, it has already covered a distance of x, and the distance left to be traveled is h minus x. I hope everyone is getting it clearly. When the body has already reached point B, it has already covered the distance x, and the distance left to be covered is h minus x. So, we always consider as potential energy on the basis of how much distance is left to be traveled. Potential energy is calculated on how much distance or how much height is still left to be traveled. In this case, that height that is left to be traveled is h minus x. So potential energy has a formula, that is mg. In place of h, now I will take h minus x because that is the distance left to be traveled. And what is kinetic energy? Kinetic energy is half mv square. But the new unknown v term is coming over here. How to solve this? Let's move back to our Newton. V square equals to u square plus 2as. Now again here, since the body initially was at rest, so the initial velocity is 0. So let's consider u to be as 0. So that is v square equals to 2as. If we use this value over here, then kinetic energy comes to be as half m into 2as. 2 to cancel. So kinetic energy equals to m. Acceleration is now gravity, g. And what is s? S, or the distance, it has already traveled. When the body is at B, it has already traveled x distance. So the s is x. That's your kinetic energy. Therefore, total energy is potential energy plus kinetic energy. So let's write mg h minus x plus mgx. Let's open the bracket. Mgh minus mgx plus mgx. So it's ultimately mgh. Okay, now let's move to the third point. That is at C. At point C. When the body is at point C, it has already traveled the complete distance or the height, that is h. Okay, at the bottom part, potential energy becomes zero. Just before touching the ground, the potential energy becomes zero. Here you have kinetic energy maximum, that is half mv square. Just before touching the ground, all energy, all potential energy has been converted to kinetic energy. So at point C, potential energy is automatically zero. And kinetic energy is half mv square. Again, we have the unknown variable v. So let's use v square equals to u square plus 2as. Considering u to be as 0, v square equals to 2as. So therefore, kinetic energy will be equals to, using this over here, half m into 2as. Cancel. Kinetic energy is m into a into s. Now, acceleration, since the body was falling due to gravity, acceleration will be gravity, and s is the distance covered. Since the stone or the particle has already came down till point C, so it has covered the complete h distance. So now this becomes kinetic energy equals to mgh. Therefore, total energy equals to potential energy plus kinetic energy. Potential energy is already zero. Therefore, total energy becomes mgh. So from this derivation, you have come to know that wherever the object may be present, along the complete path, the energy remain conserved. mgh, mgh and mgh. Clear? Along the whole path, the kinetic energy, the total energy has remained conserved. What has happened? The potential has converted to kinetic energy. Clear? Now, sometimes in school exams, they may ask what will happen after the object or the stone or whatever it is touches the ground. Remember, potential energy can only be converted to kinetic energy. And this kinetic energy then is converted to various other forms of energy like heat energy, light energy, sound energy, any energy. But potential can only be converted to kinetic energy, and the kinetic energy henceforward can be converted to various types of energy. So when the object comes and falls down on the ground, the kinetic energy will be converted to sound and heat and even light energy in case of very big objects. Okay, now with this concept, let's move forward. Let's draw a graph of total energy or the mechanical energy, you can say. So this is energy and this is your height. This is your, okay. Now, when height was 0, means when the object was near the ground, you had kinetic energy maximum. So when height was 0, you had kinetic energy maximum. And when height was maximum, you had kinetic energy 0. So this is the kinetic energy line. Clear? Got it? Now, when the height was maximum, potential energy was maximum. Let me draw a graph like this too. Potential energy was maximum. Clear? And with the decrease in height, potential energy became 0. So this is the potential energy graph. and this is the kinetic energy graph. That is the graphical representations between kinetic energy and potential energy. Okay. Now let's move to the final topic of our chapter, that is energy conservation in a pendulum. Energy conservation in a pendulum. Now, let us assume that there is a pendulum hanging like this. When the pendulum is in a rotational motion, the pendulum is swinging. Okay. Now, let's consider this to be as the ground. This is point A, the center point A, point B and point C. Point B and point C are your two extremes and A is the mean position. Let me write them down for you. A is the mean position, B and C are your extremes or extreme position. These are your extreme positions. The pendulum is swinging. When the pendulum swings, you can see that the pendulum reaches a maximum height of h from the ground. The pendulum reaches a maximum height of h from the ground. Okay. Now, what happens? At the mean position, potential energy is 0 and kinetic energy is maximum, which is equals to half mv square. At the extreme positions, potential energy is maximum, which is equals to mgh, and kinetic energy is 0 on both the extremes. Clear? So on both the extremes, potential maximum, kinetic 0, potential maximum, kinetic 0. At the mean, potential 0, kinetic maximum. Whereas if we consider somewhere between A and B, let's say this is point B, then point D has both potential and kinetic. Point D has both some amount of potential and some amount of kinetic. If it is exactly at between A and B, then potential and kinetic are 50-50. Or else there will be some more, one will be more, one will be less. If it is exactly between, it is 50-50. So now all that we have to derive is how much height can this object go, or what will be the velocity when the pendulum is swinging. Now we know that according to the conservation of energy, the energy of the mean position will be equal to the energy of the extremes. The total energy of the mean position, total energy is over here half mv square, and the total energy over here is mgh. This should match each other. These two should match each other. Let me write it down a bit more properly, clearly for you people. Total energy is equals to half mv square. Now, if we consider those two, therefore, total energy at A should be equals to total energy at B. Therefore, half mv square should be equals to mgh. Cancelling out m from both sides, you have v equals to root over of 2gh. From this formula, you can calculate v as well as h, whatever required. Okay? So that is a pendulum. Please do copy it down once. Okay, so that's all for the work per energy concepts. If you have any other doubts, do comment your doubts in the comment section. I will try to reply them as soon as possible. So we are done with our third lecture, and we will come back with the next video on the next topic very soon. Thank you everyone. Thank you all students. Have a good day.